Hi AP Calc students. This is going to be the area between the curves video. Today we had a great Zoom conference for those who had questions or just wanted to come and talk about how we're doing and what we're learning. We'll have 2 more Zoom conferences next week that you can come to if you have questions. Unfortunately, during Zoom conference, we were not able to use my document camera for me to do the problems on the Sparks worksheets that I had emailed you. So I said I'd make a video of me doing those worksheets. That's what this is. So you need your graphing calculator. Make sure it's in radians. So go to mode, make sure it's set in radians. That'll be true for all of our work in AP Calc. Anytime during the video that you need to enter something in the calculator, just pause the video so that you can do that and then go back to what I'm doing on the instructions. All right, so you'll want to enter as your y1 the f of x that we have, this whole function. And when you hit graph, that should be the graph of this curve that we see here, the curve part. If you want to change your windows so that your window just looks like that curve, then you'll want to set your x-min at maybe like -2 and your x-max up at 4 or 5, and set your y window to be going from a low of -2 and also up to 4. And then it'll look more exactly like what we have here. All right, so the first thing we want to do is find the area of the region R. So this piece right here. Well, if I think about that piece, it looks like everything came as a y equals, and it's really just the area under the curve, the area between the curve and the x-axis. So my area is going to be an integral. That's going to be this equation. So my f of x dx. And because it's the dx, my bounds on the interval are going to be x values. It's going to be from this x value to this x value. Well, clearly the one x value is going to be at 0, but how do I find this other x value? Well, I need to use the features on my calculator of going to second calculate. Option number 2 is going to be 0. So if you go to second calculate 0, you can set a lower bound when your cursor is below, and then an upper bound when your cursor is above, and then a guess, and that should get you an x value for the 0, this point right here, which comes out to be -1.373122. So the area of this region R is going to be the integral from this x value to the x value of 0 of the function f of x, which is our y1. If you put that into your calculator, that should get you an area of 2.9031. Remember, in AP Calc, we round to 4 decimal places, so 4 decimal places for any calculator answer. Okay, well, I want to talk about why I drew this little strip vertically like this. So if you remember back to area under the curve, remember this has a little width of dx, and that little bit of dx is why we used a dx in our value. And that would be the width of this little slice, and the height of this little slice is my f of x. It's my function value, or my y value for the function anywhere along this curve. And that's what this is. So if you multiply the height of this little slice, the little box, times the width of this little box, that gets you the area of my little strip, my little box here that I've drawn. And if I add all the little boxes I could draw up together here, then I'm taking the integral, I'm taking the sum, like our Riemann sum, I'm taking the sum of all of these little boxes, and that gets me my total area under the curve. So that's really a quick review of what we're doing when we take area of a region, the area of under curve, for a certain function. Okay, second part of the handout. Find the equation of line L that's tangent to the graph. Okay, well, they already gave us the point, and if you recall from today's FRQ, in addition to a point to write the equation of a tangent line, you also need the slope. Well, the slope is going to be the function, the derivative of the function at that x value. Well, on the calculator, I can do that really simply. If I use math, option number 8, that gets me the derivative, and I can find then the derivative of y1 evaluated at x equals 0, right? And so on the calculator, it looks something like this. You're taking the derivative with respect to x, you can insert y1, and x is evaluated at 0. And that should get you, when you round, it ends up at -0.5. So when I plug into the slope formula, or the point slope formula, y minus y1 is m times x minus x1, I'm plugging in my point, and I'm plugging in my slope, and it gets me an equation something like that, which we could then solve for y equals. It would look a little nicer, right? If I distribute my negative 0.5 and I add my 3 over, and there's the equation of my tangent line. Similar to what you did when you were taking an equation of a tangent line on the FRQ. Okay, at what ordered pair other than 0, 3 does the line L intersect with the graph of f of x? So in other words, they're asking, back up to our picture, this is the point 0, 3. What other point does the line and the graph intersect? So we're looking for this point right here. Maybe I call that point B. Well, again on the calculator, if I do second calculate, choice number 5, second calculate, choice number 5, that would get me a point of intersection. Before you do second calculate, of course, you'll need to enter this line that's the tangent line in as maybe a y2 on your calculator. Then you can do second calculate choice number 5. You should find that point B is going to be 3.389867, and your y value would be 1.050662. When we give answers that we might use later, don't round to 4 places. So notice I kept all of the digits the calculator gave me. That's because I have a feeling I'm going to use one of those numbers or both of those numbers in the last part, as though this was an FRQ. All right, so the last area that we're going to find is the area of region S. So again, if I look back up at my picture, my graph, I'm looking for this area. Well, that is the area between two curves because I have a graph at the top and a graph underneath. So it's the area between those two curves, which means I'm going to take the integral from my x value to the next x value where they intersect, and I need the greater function minus the lesser function. So that would look something like this. I'm going to take the integral from my first x value is 0 to the x value from point B, which is that 3.3898677, and I need to take the greater function, which is the line, which I've input as y2, minus the lower function I've input as y1, and all of that again is dx because I'm making a vertical little slice. Right? It has a little bit of width for that little rectangle I draw that has a little width of dx. All right, put that into your calculator and your answer should be 6.982 or 9820 if you want to see the fourth decimal place. All right, we're ready to start the back of your handout or the second page, page 638. And this graph's a little bit more interesting because we have a little bit more going on for these regions R and S. So I went ahead and entered into my calculator as y3, the f of x that they gave us, and as y4, the g of x that they gave us. Make sure you have a negative in the exponent spot for your g of x. And you can go ahead and turn off the y1 and the y2 that you had, but get used to not deleting those. Just turn them off by hitting enter on the equal sign. That way, if this was like the actual AP test, you'd be able to go back and check that work without re-entering equations. All right, go ahead and find the points of intersection if you need to practice that again. Here's what they should be. I called the first point of intersection for F and G to be A and the second one to be B. I marked those up in my graph, and then I found those on the calculator. So let's go ahead and find the area of region R. Before I do that, I need to figure out which graph is which equation. Which one is F and which one is G, or as I've labeled them now, which one is Y3 and which one is Y4. Okay, so I thought about which was Y3, which was Y4, and I went ahead and color-coded them for us so that we'd be able to see which function is on top for which piece of the shaded region. So when I want to find the area of the region R, I'm just going to take the integral from my x values because, again, it's one of these little vertical slices that has a little width of dx. So I'm going from 0 to the x value of A. So from 0 to 0.178218. And then I'm stacking all those little slices up, or I'm adding all those little rectangles up. And each rectangle has a height or a length of the y4, this top equation, minus y3, the greater minus the lesser function. So this is going to be my y4 minus y3 when I go to put it into the calculator, dx. Again, it's because it's the greater function for this area, this section of the graph, minus the smaller function for that section of the graph. And remember, I've color-coded them so you could kind of see which function is which. You can go ahead and just put that straight into your calculator, and that area would be 0.065. When I want to find the area of region F, I'm going to integrate. Again, it's going to have a little vertical slice like this, which has a little width of dx. So it's going to go from an x value to an x value. So the x value of A, which again was 0.178218, to an x value for point B, which is 1. And I'm doing the greater function minus the lesser function, or the top minus the bottom. And in this section, the top curve is y3 minus the bottom curve, which is y4. And all of that, of course, is dx. And you can just drop that into your calculator. You should get 0.410. All right, so now the challenging or the fun part is the last one. So we want to find the area of the unshaded region bounded by the graphs of f, g, and the x-axis. So in the picture, they're asking us to find all of this. And when you see all of that, you might recognize right away that we could split it here, because this area is underneath the y3 graph, right? And the next section here looks like it's the area under the purple curve, but that only happens until I get to here. And then I have this third little region here that is the area underneath this pink graph again. So I actually have 3 little sections that I have to add to get the area bound to the x-axis, like this. So I'm going to take the area under the curve, so under this pink curve here, which is y3, and I'm going again from 0 to the x value of point A, 0.178218. And I'm going to add to that the area under the curve, this purple one, which is y4, from the x value of point A to the x value of point B, plus, oh, don't forget your dx, plus I need to add the area going from the x value of point B of, again, that pink curve, which is y3, and I need to figure out where the pink curve is going to hit the x-axis, so I know here, we'll call it point C, of where that should stop. Well, that's the 0 of the y3 curve, the 0. So find the 0, again, on your calculator, and that is 1.0804306. And if I add all those integrals together on the calculator, my total area is 0.486. All right, that's our area under the curves using the Sparks notes. Email me if you have questions about what I posted, and it's good practice. All right, we'll see you at the next Zoom conference. I'll email you with the link.